Welcome back, everyone. We're still in section 1.3, evaluating limits analytically, and this is the third part here where we're actually going to get into evaluating some limits in a variety of different formats. So we're going to start with a table here, and then move into a piecewise example, and then look at some other examples that will require a little bit of algebraic skill. So to start, we can use the table above, and we'll want to look at our setup here. So we know that our functions are continuous. That is key. If we don't have continuity, then we have to worry about the possibility of a jump discontinuity, of course, right? So we could have a jump, which means the limit doesn't exist there. And also we could have some type of infinite discontinuity as well, right? So both of those things are going to be problematic for limits. But luckily we know that our limits are continuous, so we don't have to worry about the limits not existing. So then to start, we'll look at the first example here. Note you can add brackets around that if you want to. So it's the limit of the entire expression, f of x minus 3 times g of x, as x approaches -1. So because we know that our limits exist, we're going to just use direct substitution. So let me zoom in a little bit here. So the limit as x approaches -1 of f is going to be 5 minus 3, and the limit as x approaches -1 of g is going to be -7. Now, we could be a little more formal with this if we wanted to be, and we could rewrite this as the limit as x approaches -1 of f of x minus 3 limit as x approaches -1 of g of x. So again, we could be much more formal with it if we wanted to be, but for this example, it's pretty obvious what our answer is going to look like. So this is going to equal 5 plus 21, so it looks like we should get 26 as an answer for that first limit. Similarly, for 2, we could use our quotient property and split the limits, but I think this example is simple enough that we know that that's going to apply, except if the limit of f as x approaches 2 is 0. And what do we get? Oh, we do get an infinite limit. So it looks like if we did direct substitution, we would get -4 over 0. And so the question is, what does that mean? So what this is going to mean is that it's some type of an infinite limit. So it's going to be approaching some form of positive or negative infinity. So we're going to have some sort of an asymptote expression that results in g divided by f. But because we haven't really discussed the infinite limits yet, for the moment, we're simply going to call these non-existent. So does not exist. So this limit does not exist, and that is because the limit as x approaches 2 of f of x equals 0. So that would be our justification. So the limit of the denominator is 0, approaching 0. Okay, so we'll go to 3. So now we've got a composition of functions. So we've got the limit as x approaches 3 of f of x is equal, or of f of g of x. We could write this again as the limit as x approaches 3 g of x, and then put f of on the outside using that composition property. So as we approach 3, we're going to get 2 for g of x. So that's going to equal f of 2, and f of 2 is simply 0. For number 4, we've got the product as we approach 0. So looking at our table there, looks like we're going to get -3 for f as x approaches 0, and 1. So our answer will be -3. And then scrolling down here, now we've got some function expressions we might need to use some analytics for. We still have the table, but note we're not using f of x or g of x anymore. So these are going to be kind of standalone examples of limit evaluations. So the first thing about limits is when we see the expression for our function, the function that describes what we're taking the limit of, we can do all the same things we would normally do with a function, which is we can simplify it. And so if we take this expression, we'll get the limit as x goes to 0, and we can divide x squared out of each term there, right? So factor out an x squared in the top, and so we'll end up with 4x plus 1 as our limit expression. We'll note there's a hole at x equals 0. But for limits, so if we get 4x plus 1, it's going to look something like that. At 0, it having a hole there is not a problem, because the limit still exists at the hole because you're approaching the same value from the right and from the left. So we'll just get 4 times 0 plus 1. So our limit is going to equal 1, which of course is the y-intercept of the line. Okay. For number 6, now we have an inverse tangent of the natural log of x. So for the natural log of x and arctan, we might worry about if the natural log was undefined. We're approaching e, which is 2.7128 ... which is okay because our arctangent function, if you remember the arctan function, so our regular tangent function looks like this. We've got asymptotes, and then we repeat. Oops. Okay. But if we take the inverse of that, so we swap x and y, what we ended up with was, oops, those should be horizontal asymptotes. We end up with a graph that looks like this. So the domain of arctan is all real numbers. There's no restrictions. And for natural log, the natural log function just has to be greater than x equals 0. So we've got nice continuity here. We do need to be careful with the value we're approaching and consider both functions a little bit. But in this case, x approaching e is a legitimate value for both. And so we'll get arctan of the natural log of e. So using direct substitution, the natural log of e is just 1. And arctan of 1 is pi over 4. Note, when we're talking about arctan, it is the function arctan, which means that it has the domain restrictions of arctan, which in this case is, the range restrictions. So the range restriction is that we are stuck, if we're thinking of the unit circle, between pi over 2 and negative pi over 2, which again you can see from that graph of the arctan function as the horizontal asymptotes. Okay, so then our last example is the exponential function, which of course has a domain of all real numbers, so we don't have to worry about anything there. We can just directly substitute, and you should get 1/9 as your answer. So the more interesting examples are typically going to be piecewise functions, because we have to worry about those boundary points that we talked about last year. So what is happening, for example, at -1, right? So at -1, we've got two different arguments, and we actually have a third piece here that we have equal to a value as well. So it can be very useful to graph this. So if you want to graph this, you can graph this, of course. You've got a quadratic, a constant, a cubic, and a linear function. But really all we have to worry about, because all of these functions are continuous on their given domains, We know that quadratics, cubics, all polynomial functions don't have any sorts of discontinuities. So we just have to worry about, at those boundary points, are we equaling the same value or do we have a jump discontinuity? So let's take a look at some of these. So first one is the limit as x approaches -3, which is not a boundary point. So I just have to figure out where -3 fits into the domains here. And obviously it's going to be in that first domain. So we're going to use 4 minus x squared. So this is the limit as x approaches -3 of 4 minus x squared. So we'll just substitute. We get 4 minus 9, which gives us -5. Okay, and then similarly for b, our domain is x approaching 11, so that's going to be in our last domain. So 6 minus 5x, so we'll just go directly to evaluating that. So 6 minus 55, which is -49. So again, values not in your boundary points. For polynomials, we don't have to worry about discontinuity, so we can just use direct substitution. All right, so let's take a look then at C, D, and E. So for C, we get our first boundary point. So we've got -1, and we've got 3 values there. Now, that third value doesn't matter. So that third value is simply going to be a point in space, which if it's a hole and it has a point in space, so let's say it looked like that, the limit still exists, right, as we approach from the left and the right. So the limit would still exist. So the point value doesn't matter for the limit. It will matter in the next section for continuity, though. Okay, so we need to figure out what's happening. So again, graphically, you could try to graph it, but it's probably going to be quicker just to evaluate the limits. So in order to prove that a limit exists, so I'm going to write this down here because this is actually really important. So the limit as x approaches a of f of x equals L, using that similar definition. This is true if and only if. You might see that from time to time. So this is a biconditional, meaning it works both ways, and it has to be true. So this limit only exists if the following is true. The limit as x approaches a from the left, and we talked about this earlier, but I want to emphasize it here. As x approaches a from the right. That has to be true. So if you're proving it, this is what you must show. You have to show that those limits are the same. Okay, so let's do that for C. So we've got, we'll write it out here. So the limit as x approaches -1 from the left, the limit as x approaches -1 from the right. From the left was 4 minus x squared. From the right is this other function, 4 minus x cubed. So if we directly substitute here again, because we're continuous, we get 4 minus 1, which is 3, right? So the square changes the sign of the -1. But then for x cubed, we're going to get -1 when we cube -1. So we get 4 minus -1, which is 5. So these are not equal. Thus, the limit as x approaches -1 of f of x does not exist. So we have a limit here that does not exist. Let me separate the work here a little bit. Okay. So our final result there, though, is a non-existent limit. So what that means is we're going to have a jump discontinuity. As we approach from the left, we're going to approach 3. So at -1, so we're going to be approaching 3, and then as we approach from the right, we're going to be approaching 5. So there's clearly going to be what we would call a jump discontinuity there. Okay, so let's go ahead and move on to D. So 1.5 again is in the domain of 4 minus x cubed, so we can just directly substitute there. So it's going to be 4 minus 1.5 cubed. And what is 1.5 cubed? So let's do a quick little calculation here. 3.375. Let's actually just do 4 minus that. So we get 0.625. So that would be our value. For E, let's see, the limit as x approaches 2. Okay, so again, we've got a boundary point here between the cubic and the linear part of our piecewise function. So we'll do the same thing. So let's zoom in a little bit here. So we need to show that the limit as x approaches 2 from the left of f of x minus 4 in this case is equal to the limit as x approaches 2 from the right of f of x minus 4. And I'll just put thus down here for whatever our conclusion is going to be. So from the left, we are the cubic, I believe. Yes, 4 minus x cubed. So we'll get 4 minus 2 cubed minus 4. And we are 6 minus 5x. So we'll have 6 minus 5 times 2 minus 4. So what are we going to get here? So this is going to be 4 minus 8 minus 4. So I think it's 4 minus 12. It's -8. And then for the second one, we're going to get 6 minus 14, which is -8. Yay! So these two things are equal. Therefore, the limit as x approaches 2 of f of x minus 4 equals -8. Okay, so again, sort of a intro to using that limit notation in your work. Make sure that you show this in your work, the left and right hand limits equaling each other, if you have a piecewise function or if you have a known discontinuity in your graph. Okay. So let's go ahead and look at some graphs. So we've got a couple of graphs here. I think, let's see, I think we'll pause the video here and we'll do the next part together, starting with the applying limit properties to graphs. So we finished the second page of the 1.3 notes, and we'll be moving on now to the third page of the notes. So until next time, I'll talk to you later.